So we just want to get to that first assignment. Well, it's a long story. I moved the assignment that's the end of this part. I went ahead and moved it 2 problems up. So we'll get through the first problem, and then we'll call it quits for today. All right. So we talked about thermal energy. Okay. So thermal energy actually can either be absorbed for a reaction to occur. Thermal energy can be absorbed in order for a physical process to occur, like melting is a physical process, needs to absorb thermal energy, right? Thermal energy can be released from a chemical process or a physical process. So we are going to be tracking thermal energy. And we're going to do it using calorimetry. Calorimetry. There is something called colorimetry, which is color. So it's like anyway, you'll be doing that in Chem 2. And then there's calorimetry, like calories, and that's tracking heat or energy. So this is calorimetry. So we talked about this the other day, that if you have that cup of water and that cup of bathtub filled with the water is at the same temperature, okay? Let's just say it's 80 degrees Celsius, nice and toasty, not quite boiling. Okay, you would tell me that this cup has less thermal energy, the water in it has less thermal energy than the bathtub, even though the thermometer reads the same. Okay, and so the other day I said that the 3 things you need in order to describe how much thermal energy an object has is you need to use a thermometer to get it fixed on its kinetic energy, its temperature. You need to know a mass of the object, that kind of goes back to the bathtub and the cup, okay? The other thing then is you need to know generally, for water has something called a specific heat. So every object has its own specific heat. It's like a thermal property of the matter, okay? Specific heats or specific heat capacity, you look these up, okay? Specific heat or specific heat capacity, it's in a table somewhere. Okay, so if you want to know how much thermal energy an object has, you need those 3 things. But once we get started here, it's really kind of hard to get a fix on the exact amount of thermal energy an object has. What's easier to track is its change in thermal energy. So that's what we'll be looking at. Okay. Thermal energy and heat are synonyms. Temperature and thermal energy and heat are not. Okay, so specific heat or specific heat capacity. And this might ring a bell. Remember the other day, this is Wednesday. Remember on Monday I drew a little box, and we were actually looking at the definition of a calorie. And my little box was 1 gram. Here's my little box. Okay, that is 1 gram of substance. And remember that little experiment we said by definition what a calorie is this water raising it up from 14.5 degrees Celsius to 15.5 degrees Celsius, 1 degree Celsius. Okay, that's the same thing we're doing here when we talk about the specific heat of material. We're taking 1 gram of any material, we're going to zap it with thermal energy, zap it with thermal energy, okay, and we're going to increase its temperature up 1 degree Celsius. And actually, we're going to call that here in a minute, we're going to call that delta T, change in temperature, 1 degree Celsius. So it's a little experiment. So specific heat of something. And we're going to see that some things are more stubborn than others to heat up. Some things you got to pump up with more energy in order to raise it up that 1 degree Celsius. So specific heat or specific heat capacity, its abbreviation is C lowercase p, not SH. I don't know who does that. I don't know, physicists, biologists, I'm not sure. But specific heat is a capital C lowercase p, specific heat. Again, we look it up in a table. Okay. So kind of based upon that little experiment I showed you, hopefully this makes sense. Units of specific heat are energy per gram degrees Celsius, because remember we had to zap it with energy. 2 types of energy or 2 units of energy. There's the metric joules, and then there is the English calories. Okay, so let's see. Yep, joules per gram degree Celsius. Now these are my favorite over here. These left ones. Joules per gram degrees Celsius. Remember, the other thing we talked about Monday was that the 2 scales, the Celsius scale and the Kelvin scale, they're offset by 273.15 units, but they are like the same as it with regard to lock and step. One change, degrees Celsius, is one change in units of Kelvin. Now, over at the right there is some of my least favorite things. By the way, if I do FL, of course you know that means maybe factor label. So these work great for using working factor label problems. For whatever reason, a lot of times you'll see units of specific heat as joules/G, as in grams/degrees Celsius or Kelvin. And I just hate that one because it just drives me nuts. But that's what it still means. Joules in the numerator, grams and degrees Celsius in the denominator. All right, because it's all about units in chemistry. I am telling you. If 5 years from now you're like, I'm not sure how to work that problem, well, look at the units, okay? And let the units tell you how to work the problem. So like I said, when we talked about temperature scales, Kelvin came after Celsius, and they are both metric. They both, one unit is the same on both scales. So that's kind of nice. All right, so here are some specific heats of some material. I like to kind of, let's see, which one's the highest? Magnesium. I gotta be careful, manganese, magnesium. That one is what I call stubborn to heat up. Okay, so the way you read this, for instance, is you need to zap it 1 gram. You need to zap it with 1.024 joules in order to raise it 1 degree Celsius. That's it. Okay, it's stubborn. The least one down here is tellurium. Okay, again, 1 gram only requires 0.2202 joules of energy to increase its temperature 1 degree Celsius or 1 Kelvin. That's how that works. Specific heat. It's on a table. Here's some other specific heats. Let's see. It's not up here, but when we study the weather, one of the things that is a player in what happens in our weather is that water is very stubborn to heat up. It takes 4.184 joules of energy to heat 1 gram, 1 degree Celsius. Water is very stubborn. But the capacity part of specific heat capacity means once you've heated water up, by golly, it's like holds all this energy. Okay, so it's stubborn to heat up, but once it's heated up, if you think of your swimming pool, if you've ever had one of those above ground swimming pools or know somebody that had one, I mean, it takes forever for it to, to warm up. But once it's warmed up, it's like, there you go. Air, on the other hand, has a very low specific heat. So there have been just a few arrows in this class, and there's another arrow. So the arrows mean you need to memorize it. So actually, for water, you need to memorize the specific heat for water. I say that, and yeah, you probably do need to. But now, before we leave Unit 3, okay, Unit 3 thermodynamics, we're actually going to look at water in its other states, and it's going to have a different specific heat. So in its liquid form, its specific heat is 4.184 joules per gram degree Celsius. And we kind of looked at that on Monday, too. We said, by definition, a calorie and joule are directly related in a 1 to 4.184 units. So that's energy per gram degree Celsius. Or remember, degree Celsius and Kelvin, it's the same number. Okay. The other column then converts the grams to moles. Okay, so it's the same thing, but now the quantity is a mole of that thing instead of a gram of that thing. So you'd need what? The molar mass to go back and forth between those two. All right. So I got a couple of thought exercises here, and then we'll kind of crunch some numbers here in a minute. But notice we have 2 metals. We have copper and aluminum. We have a specific heat of copper is lower than the specific heat of aluminum. So copper is less stubborn to heat up, and aluminum is more stubborn to heat up. In these 2 scenarios, we're going to zap both of them with the same amount of energy, 500 joules of energy. Notice we have the same mass. Okay, So does it make sense that the one with the lower specific heat, less stubborn to heat up, is going to actually have a higher final temperature? Okay. So that's just kind of eyeballing it. And we're going to show you where you can come up with those numbers on your own. They both start at 20 degrees Celsius. The one with the lower specific heat, same energy, same mass, went to a higher final temperature. So you notice one thing about it is a little T sub F. We're going to be, of course, F means final and T means temperature. So little subscripts then modify or describe what the temperature, which temperature we're talking about. All right, there's another little thought scenario for you. Again, still dealing with copper and aluminum. Copper is less stubborn to heat up than aluminum. Now, in this case, we want them to go to the same final temperature. We want the delta T to be what? 30 degrees Celsius. Okay, so can you see where actually we need to add more? Now this bar down here is energy, so we're going to have to add more energy to the bottom one in order for it to get to the same final temperature. Okay, so we need to add 673 joules to the stubborn copper in order for it to go up to the same, stubborn aluminum, in order for it to go up to the same final temperature. The Q variable is coming up here in a minute. I say Q just means change in thermal energy. In this case, as I'm describing, it's energy to pump in to make that happen. All right. So like this said, you need to remember this. But like I said, and I've never thought of it until just now, this semester, it's funny how you teach something over and over again. But the specific heat for liquid water is different than the specific heat for ice, and that's different than the specific heat for steam. And we will be dealing with all of those. Specific heat of liquid water is 4.184 joules per gram degrees Celsius. All right, so here's where that Q was, right? I said Q is the amount of energy we had to pump into either one of those metals to raise it up the temperature we wanted to get the same delta T. So Q is change in thermal energy, right? So Q is change in thermal energy. M is mass. C sub P is specific heat. And we've done deltas in here before. Delta means change in. So delta T is change in temperature. I'm going to kind of break out the delta. Deltas are always final minus initial state. So here in a minute, I'm going to kind of break down what the delta means. I think this would be a great rap thing. Q is equal to M, C sub P, delta T. I'm just saying. So this kind of reminds me of in physics, you run into a lot of just plug and chug. So this is kind of an equation where you can kind of plug and chug, okay, a little bit. But we always use units, and I'll show you how the units work here. So let's look at the units. So yes, you can plug and chug, but you have to use the right units. So units of mass are going to be in grams. So I'll just go ahead and grams. I'll put G over 1. It's my mass term. Specific heat are joules per gram, either degrees Celsius or Kelvin. By the way, on the Kelvin temperature scale, you never say degrees Kelvin. It's just Kelvin units. So if you want to be really cool about it. So that's specific heat, and the change in temperature is going to be degrees Celsius, okay, or Kelvin. Okay, so let's see. Let's do our crossing out. Grams and grams cancel. Okay, degrees Celsius and degrees Celsius cancel. So we're left with units of joules, which actually is what that is. That's units of joules, and that is change in thermal energy. Change in thermal energy. Yeah. So change in thermal energy is just like I said at the beginning of class. It's like something heating up or something cooling down. That's it. Change in thermal energy. And our deltas are always final minus initial. So in this case, it's T sub F minus T sub I. Okay. So this is T sub F, and this is T sub I. And always show your work. A lot of times students won't want to show this step, but you have to show this step. Show this, please. All right. So, final minus initial, the final temperature minus the initial. Okay, so just imagine if your final temperature is higher than your initial temperature. That means that your thing of interest, your little system or whatever, has heated up, right? Okay. And actually that's going to give us a positive Q, and actually that's going to be what we call an endothermic process. If your final is less than your initial, it means it cooled down. But check this out. If your final is less than your initial, if you take something that's small and subtract something that's larger, you're going to get a negative number. That counts. One of the problems in doing these sort of problems is we kind of lose track of our sign sometimes. It really is a negative. It's no absolute value here. Okay, negative change in temperature means it's cooling down, and actually that'll give us a negative Q, we're going to see here in a minute. Okay, and actually that's an exothermic process. All right. So don't forget that since the two metric temperature scales are kind of lock and step with each other, we can basically use our specific heat scale, degrees Celsius and degrees Kelvin in the denominator. So again, like I said, if it is hotter in the final than it is in the initial, you're going to end up with a positive delta T term. Notice in your Q is equal to M C sub P delta T. Mass, always positive. Specific heat, always positive. Delta T, it can change. Your delta T then is going to drive what value your Q is, positive or negative. Okay. So I mentioned these terms, and I'll go ahead and I think they'll be coming up later. But so delta T, if your delta T is positive, that means that its final temperature is higher. And actually that means it's in what we call an endothermic process or endothermic reaction. Okay, heat has been brought in. Okay, if your delta T is negative, that can only happen if your final temperature is less. If your final temperature is less. That means it cooled down. That means it lost energy. We would call that an exothermic process or reaction. Okay. So endothermic, exothermic. Energy has been added. Added meaning in. And here energy has been released or removed. Exiting, exo. So they actually kind of go with it. All right. So let's do a problem, shall we? Using that Q is equal to MC sub P delta T. All right. So it almost seems like it needs a little picture here. Are you feeling it? I'm feeling it. Okay, so we'll have a beaker of water. I'm really just stalling there. Okay. Notice it gives us the mass of the water. So M is equal to 37.7 grams. I better say it's water because that makes a difference, doesn't it? Mass is 37.7 grams. And it gives originally at 52.0 degrees Celsius. So does that seem like T sub I initially? 52.0 degrees Celsius, and it's cooling down to 5.2 degrees Celsius. So that must be our final temperature. Okay. So we are going to use, like I said, it feels very much like physics. We're going to use the Q, change in thermal energy, is equal to M C sub P delta T. And yes, you're going to want a table of specific heats for water and or just remember the one that I told you to remember, 4.184 joules per gram degree Celsius. That's what that one is. Okay, so I guess we should look at the questions. Is the water losing energy or gaining energy? So its initial is 52.0 degrees Celsius, its final is 5.2. How many people think it's losing energy? Me too. Very good. And then this, what is the energy change of the water? That actually is Q. What is the energy change of the water? I.e., solve for Q. All right. So, here we go. Q is equal to MC sub P delta T. Now, sometimes, though, we're after a different variable. This one is like probably the easiest of all of them to go after. You figure there's, what, 4 variables up there? And sometimes you don't know something else. Okay. So the mass is 37.7 grams. The specific heat for liquid water is 4.184 joules per gram degree Celsius. See what I mean? I hate that. We're just J/G/degree Celsius. Delta T, I told you need to show this. So here's the little kind of pre-calculation. Delta T is T sub F minus T sub I. In this case, it's that cooler temperature, 5.2. Now notice, and I think you've probably seen me do this before, if you have two numbers with, and I guess if you're adding or subtracting them and they have the same units, you actually can put the numbers in parentheses and then put the units outside. So our final temperature was 5.2 degrees Celsius minus 52.0 degrees Celsius. That's our initial temperature. So we have a negative temperature, right? Negative change in temperature. And we said that was exothermic, which doesn't seem like it's releasing energy. And don't forget, when we do subtraction, we round according to decimals. All right, so let's plug them in. Make sure we use the units, though. And I kind of like to put things over 1 so that things cancel, right? So I would put the mass term, 37.7 grams, over 1. And then I would introduce the specific heat, 4.184 joules per gram degree Celsius. And then stick in that negative delta T, negative 46.8 degrees Celsius. And of course, when you're working physical science problems, make sure things cancel, units cancel, grams cancel, degrees Celsius cancel, and you have units of joules, which is right. And it looks like we need to round according to 3 significant figures. Okay. So I went ahead and packed it up in scientific notation. Do you have to? No, but I did. So negative 7.38 times 10 to the 3rd joules. A lot of times these energy or these thermodynamic problems, they will want you to leave it not in joules, but go to kilojoules for whatever reason. Okay, I think I do that down here. I don't, yeah. So it didn't say it. So you could leave it in joules or you could take it all the way to kilojoules. So all I've done here is to take the negative 7.38 times 10 to the 3rd joules, and to get it to kilojoules, I recognize there's 1 kilojoule and 1,000 joules. So then joules cancel, and we're left with negative 7.38 kilojoules. That's it. Now there's a little bit of semantics, I guess I'd call it, with regard to thermodynamic problems, expressing the answer. So we could say that the energy change of the water was negative 7.38 kilojoules, just like we got. Or, instead of kind of saying the negative, we could say the negative indirectly, and we could say that 7.38 kilojoules of energy was released or lost. Okay, and in that sense, we are actually saying it's exothermic and it's a negative Q. I guess what you wouldn't want to say was negative 7.38 kilojoules of energy were lost, because then you'd be like, well, negative was lost. So, yeah. All right, so these are the problems. We'll take a quick look at them. that I brought in from the last slide, so these will be due on Monday, right? 7.1 and 7.2 only. And they're fun. Wonder if there it is. It's mislabeled, but. Okay, so very kind of busy or whatever, but it's similar to what we did although it does take it up a notch. Okay, so what is the heat released in kilojoules? What is the quantity of heat in kilojoules, excuse me, not released, but required to raise, they give the volume of water. Now, in this case, like I say down here, you're going to get the mass from the volume, which was 9.25 liters, and the density of water. Okay, so that's the only catch there. That should be fine. And then B, it's a different problem. They give you it's aluminum instead of water. They give you the mass of aluminum, and actually they give you the specific heat of aluminum. And again, you're solving for Q as this thing cools down. So in this case, they don't give you the initial and the final temperature. They give you delta T. But you have to look up the specific, no you don't, the specific heat's given the problem, yeah. Yeah. And the next one looks like this. So now you're after a different variable. So we're still going to use Q is equal to MC sub P delta T, but now we are after, boy, I'm a fast writer. Now we're after the final temperature. Okay, so here in purple, I've kind of outlined what we know about the story problem. In purple, they gave us the mass of the water. They gave us the initial temperature, 22.9 degrees Celsius, but they don't give us the final temperature. Over here, also in purple, they give you Q, basically. They say how much energy was added, 8.75 joules. It seems like the temperature's going to go up. Okay. So you have to basically... what I usually do is leave it Q is equal to M C sub P delta T. I basically plug in these variables or rearrange it and solve for delta T. Okay, come up with delta T and then do one last look at what delta T is. It's the final, which we are solving for, minus the initial. So that makes sense. Cool. I think that's it. Wait, is there more? Oh, there is another one. Okay, platinum now, and again they're saying you're supposed to solve for the final temperature, so it's kind of a similar thing. Okay. All right, they're like little brain teasers. Okay. Yes, ma'am.
SPHT specifically.
SPHT.
At the end of B in parentheses.
Yes, that should have been, that's C sub P, yep, specific heat. Yes.
And
Okay.
it's in like kilocalories, so we're going to...
Kilocalories, oh yeah, yep,
Kilocalories.
that's true, good catch. It's not the joules that we all know and love, it's calories. Yep.